We're doing page 16, the last page of integration. For number 9, it says, show that this rational function can be rewritten in this form. And to do that, we're going to do a trick which may remind you of completing the square. Okay? And you might not see why we're doing this at first, but afterwards you'll see why. You see I've rewritten this function here as 4x minus 4 plus 1 divided by x minus 1. You see the orange part is basically I'm adding 0. I'm subtracting 4 and then immediately adding it back. So, but why am I doing this? Because if I put that convenient negative 4 in there and then I group them like this, then you can see that the 4x minus 4 actually can be factored, and it could be 4x, right? Okay, and then we could separate it out. We say, oh, 4x minus 1 divided by x minus 1 is one term. The other term would be 5 over x minus 1. And now you can see that these cancel out, and you end up with 4 plus 5 over x minus 1, which is what they wanted us to show. And so then they say, okay, now show that the integral of this function is this kind of complicated looking thing here. And so basically, since it's so difficult to find an integral of one function divided by another, we don't have a quotient rule for integration. What we can do is we can divide it up into these two terms. We can divide it up into the 4 term, and we can put also the 5 divided by the x minus 1 term. And if we do that, then we have two easy integrals to do. One would be, the integral would be 4x, and the integral would be log of x minus 1, 5 log of x minus 1. And then we're going to evaluate, we do the definite integral, evaluating that from the limits 3 to 5. So then we would just have, with like 5 in there, we'll get 20 plus 5 log, natural log of 4. If we put 3 in there, then we're going to get 12 minus 12, and then the other one is going to be 5 natural log of 2. Okay, and then, let's see. Then we can group these terms. 20 minus 12 is going to be 8. And then we can group these terms. 5 natural log of 4 minus natural log of 2. And it turns out that natural log of 4 minus natural log of 2 is the same thing as natural log of 4 divided by 2. So that's equal to natural log of 2. Okay, so this is like heavily uses stuff from chapter 4, which I'm not sure you were comfortable about it in chapter 4. So now using it here is going to be pretty difficult to remember. But just remember that one of the properties of logs is if you have the log of something plus the log of another thing, that's equal to the log of the product. And if it's a subtraction, then it would be log of the quotient. Okay. So, going on to the next one, number 11. Evaluate the following integrals using area interpolation. So now, a really weird looking function like this with squares and diagonals, this is not going to be something that you're going to take the antiderivative of and find a nice function using the few integral rules that we have. So you're going to interpret the integral as basically calculating the area, and since it is a square and diagonal function, it is easy to calculate the area because you know how to calculate the area of triangles and rectangles, right? So, let's see, how many whole rectangles or whole squares are there here? There's these, right? And oh, you know what I'm going to do? I'm going to do the positive ones in green, and I'll do the negative ones in red. So we have about 5 whole. No, they're not whole, are they? We have about 4 whole squares here. And then we have some partial ones, right? And then, like, for the negative ones, we have 3 whole ones there, 2 whole ones there, 2 whole ones there, and then we have a few partial ones. Okay. Now let's figure out A. So it says from 0 to 3. So that would be the integral from, or the area from here to here. we have 4 whole squares, plus we have 1, 2, 3, 4, 5 partial squares, which are all triangles. So it would actually be, we'd actually do half of those 5. Okay, and if you don't believe me, just complete the rectangles here. You can see that we have 5 partial squares of these 5 squares. So the 5 squares would be halved, and then you would get 2.5, right? So 4 plus 2.5 equals 6.5. What about from 2 to 4? 2 to 4 would be interesting. That would be these two. So now you can see we're combining positive regions with negative regions. So we're going to combine 3 partial yellow squares with 3 partial orange squares. So actually those would cancel out exactly, and we would just get 0. You see how there's 1.5 yellow squares here, and there's 1.5 orange squares, which the orange squares are negative, the yellow squares are positive, so they would just cancel out and you get 0. You could write that out as, it would be 1.5, positive 1.5 minus 1.5 is equal to 0, for example. Okay? If you wanted to draw that out a little bit better, you can see that, like the yellow squares here, that's half of 3. The orange squares here is half of 3. So that's why you get 0 there. Alright, 12. Evaluate the following integrals using area interpolation, interpretation. And so here, first thing it says is that once the area from 0 to 4, that would be this area here. You can see that that is a circle. We know how to calculate the area of circles. The radius of the circle is 2. It's half of a circle, not a whole circle, so it would be half of pi r squared, which would be 1/2 of pi, and r is 2, so it would be 4, right? So it would be 2 pi. And then this one here, it's 6 to 8. It's a smaller circle, radius of 1. So, and it's a half circle also. So it would be 1/2 pi r squared, and the radius in this case is 1. So it would be 1/2 pi, and the radius is 1. So that would be the answer right there. Okay? Those types of problems are really popular on the paper 1 exam, because they're things you can do without the calculator, and they shows you that you understand that the integral is actually finding the area under a curve. Right, as a single integral. So we can use some of the properties that we were looking at before, where, remember, if you have the integral from 2 to 4 and the integral from 4 to 7, that's of the same function. Basically, that's the same thing as finding the integral from 2 to 7. Right? Because if you're going to find the area, let's say you have like a function like this, and you have some x coordinates here, 2, 4, and 7. And if you found this area that's red and you found this area that's orange, isn't that the same thing as if you found the area from 2 through 7 and all at once? Yeah, if you added the red area with the orange area, it's the same thing as finding the area of the blue region, right? And so this is the blue region here, and this is the orange area here, and this is the red area here. So you can see physically what we're adding there. Okay, number 14. If the integral from 1 to 3 is 2, and the integral from 1 to 6 is -3, find the area from 3 to 6. Okay, so basically, if we have the integral from 1 to 3, and we add it to the integral from 3 to 6, just using the property that we just showed, that's the same thing as having the integral from 1 through 6, right? So let's say, if integral from 1 to 3 is 2, the integral from 1 through 6 is -3, then what is the integral of 3 through 6? Okay, so using a little bit of algebra there, we can see that the answer is going to be -5, right? If we put a -5 in this box, then that would work out. So, -5. All right. if g of 2 equals 4 and g of 3 equals 5, calculate the integral from 2 to 3 of the derivative of g minus 1. Okay, so this looks a little bit difficult, but let's see. First thing, let's try to take the integral of this expression here. So the integral of g dash, of g dash x minus 1. So the integral of g dash, of course, is just g, right? The integral of a derivative is the function itself, right? And then the integral of negative 1 is negative x. So then we can now evaluate the function like this. So g of 3 minus 3 minus, and then we evaluate the whole thing with 2. So g of 2 minus 2. And so g of 3, they just told us 4. So 4 minus 3. G of 2, they told us, g of 3, they told us is 5. So it's 5. G of 2, they told us is 4. So it's 2 minus 2 is equal to 0. And that's it for this chapter.